So looking at thermal energy from the microscopic perspective, the behavior of the individual molecules. We know each molecule has a certain number of modes, and those modes are just ways to have energy. So each molecule has, have you been using a specific variable for a number of modes or just writing out a number of modes?
In the textbook, I think they're just writing out number of modes.
Okay, let's be consistent about that then. So number of modes per molecule. So number of modes is specifically the number of modes per molecule. And each one of those modes has how much energy? If you wanted to know how much energy a single mode has, yeah, 1/2 kBT. So the 1/2 kB is just a constant of proportionality. And then T is the temperature. This is essentially the equipartition theorem written in the form of an equation. Equipartition theorem is that everything's at the same temperature. If it's at thermal equilibrium, all the same temperature throughout, then every mode has the same energy. The energy is distributed evenly to all the modes. And that's an on average thing. It doesn't mean every mode has the same energy all the time automatically. It's just that there's no reason to expect one mode to have more or less energy than any other if everything's at the same temperature. In fact, this is ultimately what at the same temperature means. When we say two substances are at the same temperature, we're saying that they have the same average energy per mode, which means that the energy per mode depends only on temperature, and it is in fact just the temperature times this conversion constant. The 1/2 kB, which is measured in units of joules per Kelvin, is essentially a conversion factor for converting the temperature to the average energy per mode. But that's just for one mode. A typical molecule is going to have several modes, maybe 3 or 5 or 6 or 7, or maybe lots of them if it's a more complicated molecule. So how do we go from the energy in one mode to the energy in the entire molecule?
Number of modes times like the number of moles or Avogadro's.
Just for one molecule, though. If we're looking at just one molecule, how would we find the energy of that one molecule? This is the energy of one mode, right? How do we convert that to the energy of, yeah, we multiply by the number of modes per molecule. If we take that 1/2 kBT, that's the energy of one mode. If a molecule has, let's say, 5 modes, we would just multiply this by 5 to get the energy in those 5 modes. Or more generally, the energy in one mode times the number of modes. Because if you think of this as energy per mode, and then you multiply by number of modes and modes cancel out, and you just get the energy. I guess formally this should be thought of as modes per molecule. So you multiply energy per mode times modes per molecule. Modes and modes cancel out. We're left with energy per molecule. So this formula will get us the energy in one molecule, just building up from the energy per mode and then expanding that to several modes in the molecule. Any questions on that so far? And this would get you the energy in all the modes in the molecule. Sometimes it's useful to focus on just certain types of modes. Like if you wanted to know, for instance, how fast a molecule is moving, what are the only types of modes you'd care about if you want to know how fast a molecule is moving? What are the only types of modes? Yeah, the kinetic energy modes. And if we care about motion through space, we specifically care about the translational kinetic energy modes. We could ignore the rotational energy modes unless we want to know how fast it's spinning. So to look into the molecular speed, the speed of one molecule as it moves, or average speed of a molecule, we would look at only the kinetic energy modes, only the translational modes, translational kinetic energy modes. And how many translational kinetic energy modes would one molecule have? Yeah, 3 translational kinetic energy modes per molecule. So that means the kinetic energy of one molecule is 1/2 kBt times 3. Even if the molecule has more modes of other types, rotational modes, internal vibrational modes, external vibrational modes, if we're just looking at how fast a molecule is moving, all we care about is the translational modes. So the kinetic energy of one molecule on average would be 1/2 kBt times 3, because there's only 3 translational modes in that molecule. So that'll be 3 times 1/2 times kb times t. So we can use this as a formula for the kinetic energy of one molecule. And what's the only thing that depends on? Yeah, the only variable in this entire equation is temperature. So the kinetic energy per molecule depends only on temperature. If 2 substances have the same temperature, then they're guaranteed to have the same average kinetic energy per molecule, no matter what the molecule is, or what phase it's in, or anything like that. The only thing that matters is the temperature. However, does same kinetic energy mean same speed? Not necessarily, because kinetic energy involves speed and also what else? Right, mass. Kinetic energy, our usual formula for that is 1/2 mv squared. So if we set these equal to each other, 1/2 mv squared equals 3/2 kBt. Same temperature means same 1/2 mv squared, but the particles might have different masses. If the molecules are the same mass, like if it's the same type of molecule, for instance, then same temperature does mean same speed. But if they're different types of particles with different masses per particle, because this should be mass of one molecule, the molecular mass, then that's going to mean different speeds. You could even solve for speed, though. If you just set these equal to each other, you can immediately cancel out the 1/2. So you get mv squared equals 3 kBt. And then how would you solve that for speed? Yeah, divide by mass. Take the square root. So the speed of one molecule is square root of 3 kb times temperature of the substance divided by mass of the molecule, which means that the speed depends on the temperature and the mass. The 3 kb is just a constant, so that doesn't really change from one molecule to the other. But the speed of a molecule depends only on the temperature of the substance and the molecular mass of the material. So 2 substances that have the same temperature could have different molecular speeds if the molecules are different masses. Any questions on that so far? And by the way, where could you find the molecular mass? If you want to know the mass of a molecule, like let's say water, for instance. If you want to know the mass of a water molecule, what would you do? Or where would you find that?
The periodic table?
Yeah, periodic table lists out not only the atomic number, but also the mass of the atom. So look up mass of oxygen, I think that should be 16. Mass of hydrogen, 1 each. So 16 atomic mass units, 1 atomic mass unit, 1 atomic mass unit. Add those up, we get 18 atomic mass units. Atomic mass unit basically being the mass of 1 proton or 1 neutron. And if you have exactly 1 mole of those, I think that works out to 1 gram. Any questions on that so far? All right, then let's see if we can expand from 1 molecule to many molecules. Because you'll never really be dealing with just 1 molecule. Usually we've got lots of molecules we want to build up from one molecule to many molecules. So let's say instead of having one molecule, you have n molecules. Oh, and our usual standard here is we typically use capital N for number of particles, molecules or atoms or whatever, and lowercase n for number of moles. So little n, number of moles of the substance, capital N, number of particles in the substance. And what's the conversion factor between those? Like if you know how many, if you know you've got 5 moles, how would you figure out how many particles? Yeah, multiply by Avogadro's number. So to convert between those, number of moles times Avogadro's number tells you the number of particles. Because this is really just number of moles times, and then Avogadro's number is literally just the number of particles per mole. Particles per mole. Moles and moles cancel out, you get number of particles. So you can essentially treat Avogadro's number as a conversion factor here. So if we have capital N molecules, then we know this is the energy of one molecule. This is energy per molecule, or per atom, per particle, whatever type of particle it is. What would we have to do to that to scale it up to many molecules? Yeah, if we just multiply
by Avogadro's number again.
Not necessarily Avogadro's number, but just the number of molecules in the sample. If we use Avogadro's number, we'll get the energy for exactly 1 mole, which can also be useful. But generally, you'd multiply by the number of particles in the sample. Because if we're taking energy per molecule and we just multiply by number of molecules, molecules and molecules cancel out, and we get the energy of the whole sample. So generally, if you have a sample and you know how many molecules it has, you can calculate the thermal energy by just multiplying energy per mode times number of modes per molecule times number of molecules in the whole sample. Modes and modes cancel out, molecules and molecules cancel out. You're left with just the thermal energy of the whole sample. Any questions on that so far? Alternatively, another way we could write this, instead of writing it in terms of molecules, we could write it in terms of number of moles. N particles means little n times Avogadro's number particles. So we can replace number of particles with Avogadro's number times number of moles. If we just make that substitution, now instead of talking about big N molecules, we're talking about little n moles. So we now have a formula in terms of number of moles instead of in terms of number of molecules. This is often more practical because typically moles is the information you have, the information you would measure in a laboratory setting. So if little n is the number of moles, the size of your sample measured in moles, this formula will tell you the thermal energy of the whole sample. And it is just the kinetic energy and potential energy of all the modes, but all that combined, the energy in all the modes combined is the thermal energy of the whole substance. Microscopically, we call it the kinetic and potential energies of the individual molecules. Macroscopically, we just describe it as the thermal energy because it does depend on temperature. Any other questions on that so far? So this formula would be sufficient, but we can take this a couple steps further to make the algebra work out much more conveniently. Specifically, we have this combination here of the very, very, very small Boltzmann's constant times the very, very, very large Avogadro's number. Boltzmann's constant is essentially talking about the energy in individual molecules. So naturally, it's going to be very, very small. Avogadro's number is the number of molecules in 1 mole. So naturally, it's going to be very, very large. But when we combine those, the very, very, very smallness and the very, very largeness mostly cancel out, and we get a much more reasonably sized number. Specifically, a number called R. So R is defined as Boltzmann's constant multiplied by Avogadro's number. Anytime you got Boltzmann's constant multiplied by Avogadro's number in any sort of formula, that can be abbreviated as R. And you've actually seen R before. This is the same R you've seen in the ideal gas equation. R is called the ideal gas constant. So ideal gas constant is defined as Boltzmann's constant times Avogadro's number. Or to put it another way, you could say Boltzmann's constant is defined as the ideal gas constant divided by Avogadro's number. I think the ideal gas constant may have been defined first, so really we should be saying Boltzmann's constant is defined in terms of Avogadro's, or in terms of the ideal gas constant, but you can define it either way. I usually think of these as like ideal gas constant and Boltzmann's constant. They're basically talking about the same concept, the idea of converting temperature into thermal energy. The difference is Boltzmann's constant is talking about energy on the level of individual molecules. Ideal gas constant is talking about energy on the level of entire moles of molecules, which is why the conversion factor is Avogadro's number. We're essentially scaling up from information about individual molecules multiplied by number of molecules in a mole, and we get information about entire moles. So same idea, just using different units of measurement. Energy per molecule versus energy per mole. Any questions on that so far? The ideal gas constant, yeah, this idea of this formula we've got so far is valid no matter what the phase is. This should work for solids, liquids, and gases. We call this the ideal gas constant because it shows up in the ideal gas equation. But this formula for thermal energy is perfectly valid for solids, liquids, and gases. The only thing that's going to change is the number of modes per particle. So let's tidy this up. We've got Kb times Na is R. We also need to include times temperature. We need to include times number of modes. We've got a 1/2 we need to include there. I'll just put that as A divided by 2. So we're taking care of the 1/2, the T, number of modes, Kb times Na is R. We still need also a times N. So this gives us a much tidier, more compact formula for thermal energy. Very convenient. And again, this works for any substance, no matter what phase it's in, no matter what type of chemical it is. The thermal energy is just number of moles, how much of the substance there is, times R, the ideal gas constant, times the temperature of the substance, times number of modes per particle divided by 2. And that should be really an average number of modes per particle. It's possible that the particles don't all have the same number of modes. Maybe you've got, for instance, a diatomic gas that's hot enough that some of the molecules have their vibrational modes active, but the other ones don't. Molecules with the vibrational modes active would have 7 modes. If the vibrational modes are frozen out, they'd only have 5 modes. If you've got some of each, the average is going to be somewhere in between 5 and 7. But any given molecule will have a whole number of modes, but the average might not be a whole number. Any other questions on that formula so far? And just like any formula with multiple variables, if you know all but one of these, you can solve for that missing unknown. For instance, let's say you know the thermal energy, and you know the temperature, and you know how much of the substance there is. What would be the only unknown left?
The number of modes.
Number of modes would be the only unknown left, so you could solve for that algebraically, and that gives you some very useful information about the substance. In fact, this is even more practical if we apply a delta to it. Delta E thermal equals, what's the only part of this that you would expect to change if you add energy to the system?
The temperature.
Yeah, the temperature is presumably going to change. You're not changing how much of the substance there is. you're probably not changing the number of modes unless you're adding so much heat that you activate modes that were previously frozen out. So we would generally assume number of modes is constant for small changes in energy. So we can factor out everything else as constants. N is a constant, R is a constant, temperature is presumably changing, and then number of modes would probably be constant. So we now have a formula for a change in thermal energy, which would presumably just be the heat you add. So you add some heat, the temperature changes, and you can then calculate, if you measure how much heat you're adding, and you measure the amount the temperature changes, and let's say you know the number of moles, you can figure out how much of the substance there is by measuring how much space it takes up, for example. If you know those quantities, you can solve for number of modes. So everything else, the thermal energy, the number of moles, the change in temperature, all these can be found experimentally in a laboratory setting if you've got the right tools for it. Which means number of modes is the only unknown left. Solve for that algebraically. And let's say you calculate the number of modes. Let's say you find that number of modes and it happens to be 5. So let's say you've got a container full of gas, you do some experiments on it, you measure all these values and you calculate the number of modes and you find that the result is 5. What does that tell you? If you know the number of modes is 5 per molecule, what does that tell you about that molecule?
It's a diatomic gas with some modes frozen out.
Yeah, or not necessarily diatomic. It could be polyatomic as long as its shape is what?
As long as it's linear.
Presumably 3 of them have to be translational. What would the other 2 be?
Rotational.
Rotational. And if it has 2 rotational modes instead of 3, it doesn't have to be diatomic, but it has to at least be what shape?
Non-linear.
Nonlinear would be 3. Yeah, linear would work. Nonlinear would be 3 because if it's not a straight line in shape, if you've got a nonlinear molecule, it can rotate around the x-axis and the y-axis and the z-axis. But if it's linear in shape, rotating around its own axis of symmetry doesn't actually change anything. So linear in shape would mean 2 modes per molecule, 2 rotational modes. So if you measure the heat, number of moles, and temperature change, and you calculate that there's 5 modes per molecule, you know that that gas molecule is linear in shape. You can calculate information about the shape of the individual molecules just by adding heat and watching how its temperature changes as a result. A macroscopic experiment that gives you information about the microscopic world. And this, again, was one of the big pieces of evidence suggesting that atomic theory really is true, that matter really is made up of tiny particles called atoms and molecules, because the behavior that is predicted by this theory matches the behavior we actually measure in experiments. Any questions on that so far? So let's take a look at a couple other things we can do with this big formula. We have thermal energy is N times R times T times half the number of modes. Or you could look at this in terms of delta thermal energy equals N times R times change in temperature times half the number of modes. And there are some very useful other substitutions we can make here. One of them, where else have you seen nRT before?
PV equals nRT.
Yeah. The ideal gas law, or ideal gas equation, tells us that for gases, at least well-behaved gases, pressure times volume equals number of moles times ideal gas constant times temperature. Since nRT shows up here, and we also know that nRT equals PV, pressure times volume, we can make this substitution. And this substitution only works for gases. This formula we have so far, this thermal energy formula, works for any substance, no matter what phase it's in. But if the substance is a gas, a well-behaved gas, an ideal gas, then we can make this substitution. nRT can be replaced with PV. So we get thermal energy equals PV times number of modes over 2. And this is a very interesting formula, very different formula, because it's a formula for thermal energy that is now missing what variable? What variable does not show up in this equation anymore? Yeah, this is a formula for thermal energy that does not include temperature. The temperature is kind of baked into the pressure times volume. It's just hidden. But it means you don't need to know the temperature in order to calculate the thermal energy. If you're dealing with an ideal gas, you can measure the pressure, how tightly packed it is. You can measure the volume, how much space it takes up. And if you know the number of modes, you can calculate the thermal energy without needing a thermometer at all. And this is going to be very convenient when we get to pressure volume graphs. We're going to be describing the behavior of gases by drawing a graph, volume and pressure, and then looking at what happens to a gas as its volume and pressure change. So you're going to be seeing a lot of graphs like this in the coming weeks. And if you know a point on this graph, you know the volume, you know the pressure, and you can calculate thermal energy without stopping to find the temperature first. All you need to know is pressure and volume, and number of modes, of course, and you immediately know the thermal energy. Any questions on that so far? And of course, we could also convert this to a delta thermal energy as well. If we want to write this as change in thermal energy, what could be changing on this side of the equation as you add heat?
The pressure?
The pressure could be changing. Like, let's say you've got this in a box and you add some heat. As the temperature rises, the pressure could be increasing. Could the volume be changing?
Yes.
Yeah, the volume could also be changing. Maybe you've got a balloon that can expand, or maybe you've got a rigid box, but it's got a piston that can rise. So the volume could be changing and the pressure could be changing. We can't really pull either one of them out as a constant. So we would have to write this as delta P times V times number of modes over 2. And that delta P times V should be interpreted as the final value of pressure times volume minus the initial value of pressure times volume. So for instance, on this graph, you'd have the final value of pressure and volume multiplied together minus the initial values of pressure and volume multiplied together. You can't really split that up into like just the change in pressure or just the change in volume, unless one of them is constant. Like if you know the volume is not changing, you could write this as delta pressure times the volume. Or if you know the pressure is constant and the volume is changing, you could factor out the constant pressure and say pressure times change in volume. But we have to consider at least the possibility that they could be both changing, in which case you can't split this up any further other than just final pressure times volume minus initial pressure times volume. Any questions on that so far? And again, this version of the formula works no matter what phase it's in. This one only works for gases, but it's a very convenient shortcut if you're dealing with gases. And someone was mentioning heat capacity earlier. Let's see how this connects to the idea of heat capacity that we were looking at much earlier in the quarter. We have a, let's call this the microscopic formula. But at the beginning of the quarter, we were also looking at a macroscopic formula for thermal energy. The formula we were looking at the very beginning. What was the very first formula we used for thermal energy at the very beginning of the quarter? Yeah, MCT. And of course, we were calling it delta E thermal equals MC delta T. But if we strip off the deltas, this is just the thermal energy is mass times specific heat times temperature. By the way, if there's no delta there, if it's just a raw temperature variable and that's it, what units of measurement does that have to be in? Yeah, that's got to be in kelvins. If it's a delta temperature, you can use Kelvin or Celsius as long as you're consistent about it. A change in Kelvin and a change in Celsius are going to be the same value. But if it's just temperature without a delta attached, it has to be in Kelvin because that's the one where 0 actually means something. Like if you say 200 degrees Celsius, you're just saying it's 200 above and beyond some reference point, freezing point of water. If you say 200 Kelvin, that actually means there is 200 of something, 200 units beyond absolute 0. So we've got a formula for thermal energy from the macroscopic perspective and a formula for thermal energy from the microscopic perspective. They're really the same thing, though. It's not like this is talking about two different kinds of thermal energy. We just have two different formulas for the same thing. And anytime you've got two different formulas for the same thing, what can you do with those formulas?
You can set them equal to each other.
Yeah, we could set these formulas equal to each other and then see what we get. One thing we want to do first, though, this formula is describing how much of the substance there is in terms of mass, number of kilograms. This formula is also talking about how much of the substance there is, but it's describing it in terms of number of moles. We don't want to be messing around with different units of measurement here, so I'm going to make an adjustment here. Instead of talking about mass times specific heat per kilogram, I'm going to rewrite this as number of moles times the molar specific heat. So number of moles is also a description of how much of the substance there is. But then instead of using specific heat in joules per kilogram Kelvin, we're going to use the molar specific heat, which would be measured in joules per mole Kelvin. Same idea, just using different units of measurement to match up with the idea that we've got moles here. And this is why if you take a look at a data table of specific heat values, it typically lists two different values for each substance. One value in joules per kilogram Kelvin, one value in joules per mole Kelvin. We're just using the joules per mole Kelvin so that it cancels out number of moles. Same idea, just different units. So if we set those equal to each other, we can say E thermal from the microscopic perspective equals E thermal from the macroscopic perspective. Microscopic perspective, we'll use this formula. Macroscopic perspective, we'll use this formula. And what can we simplify? How can we simplify this equation?
You can cancel out the number of moles.
Yeah, N shows up on both sides, so we can divide by number of moles, cancel that out. What else shows up on both sides here?
Temperature.
Yeah, we can divide both sides by temperature. Or even if we had written it in this format, we could still just divide both sides by delta temperature and it would still work. So we're left with R times number of modes over 2 equals the molar specific heat. So we now have a formula for molar specific heat that explains why different substances have different specific heats. The only thing that determines molar specific heat is the number of modes per molecule, since R and 2 are constants. So molar specific heat is proportional to number of modes per molecule. Or per particle, since they might be molecules or atoms. And the constant of proportionality is just R over 2, ideal gas constant over 2. So we can use this to rapidly predict what molar specific heat we should expect for any substance we want. As long as you know the number of modes, you can just multiply that by R over 2, and that tells you the molar specific heat. Or that also works in reverse. If you know the molar specific heat, which you can measure experimentally, you can multiply by 2, divide by R, and that tells you the number of modes per particle. So that's a very nice connection between the macroscopic measurement and the microscopic reality, what's actually going on at the molecular level.
So then shouldn't we see like very similar number of modes for, I don't know, argon and helium?
Yeah, exactly. Let's try that out. If we're dealing with an ideal gas, a monoatomic gas, let's see if we can predict what the specific heat should be. So monoatomic gases, which really should only be happening if we've got a noble gas. Helium, argon, xenon, etc. Any monoatomic gas. How many modes does that have per particle?
3.
Yeah, it's got the 3 kinetic energy translational modes and nothing else. Each atom, because it is monoatomic, has 3 modes. Translational kinetic energy in 3 dimensions. No rotational modes because a single particle can't really vibrate or can't really rotate. No external vibrational modes because it's a gas. There's no nearby other molecules to vibrate against. No internal vibrational modes because a single atom doesn't really have an interior in a meaningful sense. So that means the molar specific heat should just be R times 3 over 2. R is what, about 8.3-ish, 8.31? Is it 8.31 or 8.13? I forget.
8.31.
Thank you. And I believe that is joules per Kelvin mole times 3 divided by 2. Punch that into your favorite abacus or calculator. And we get molar specific heat is about, that's not right, divided by 2, about 12.465 joules per Kelvin mole. So we can predict that the molar specific heat for any noble gas should be about 12.4, 12.5-ish. And if you look that up, that should be pretty close to what it is. Let me see if I've got that in here. Are these not listed in noble gases? Anyone happen to have the molar specific heat of helium on quick recall? I don't either, but it should be 12.465. You can look that up if you want to check. But let's try another molecule. Let's say diatomic gases, for instance, maybe oxygen or nitrogen. Such as N2 or O2 and so on. How many modes would we expect that to have?
Total.
What was that?
7.
It could have up to 7. Under what circumstances would it have actually all 7 of them?
Probably at a higher temperature.
Yeah.
Where it's not all frozen out.
Right. At a very high temperature, then all 7 modes would be active. You got the 3 translational modes as always, plus 2 rotational modes because it's linear in shape, plus 2 internal vibrational modes because those atoms could be vibrating against each other inside the molecule in 1 dimension. So those 2 internal vibrational modes are 1 kinetic, 1 potential. So what if it's colder temperature, like let's say about room temperature? If we're at a more medium temperature, what would you expect about the modes?
Maybe like 5 modes.
Yeah, 5 modes because what's missing?
Vibrational gets frozen out.
Yeah, the vibrational modes are only active at very high temperatures. At more medium temperatures, like around room temperature, we would expect the vibrational modes to be frozen out, and so only the translational and rotational modes would be active. So around room temperature, we would assume the vibrational modes are frozen out. They're not active because there's not enough energy to make them vibrate. So we'd only have the 3 translational and 2 rotational. Or if it's very cold, the rotational modes might also be frozen out. So at very low temperatures, how many modes would we expect?
Like 3.
Yeah, we'd expect only 3 modes at very cold temperatures. Because you'd have only the translational modes, everything else would be frozen out. So that means since we've got these 3 different options for number of modes per molecule, we're also going to have 3 different options for molar specific heat. We're going to have R times 3 over 2, or R times 5 over 2, or R times 7 over 2. So if we try each of those, let's see what we get. 3R over 2 we already found is about 12.4. I'll say round up to 12.5. If we got 5 modes per particle at more room temperature range, we'd have 5R over 2. Or at very high temperatures, we'd expect it to max out at 7R over 2. If we try calculating each of those, we get 5 times 8.31 over 2 is about 20.8. And then 7 times R over 2 is about 29.1. And if we check that on the list, because I actually have oxygen and nitrogen on this list, I don't know if this is going to be visible, but oxygen, nitrogen looks like about 29.04 for nitrogen and 29.16 for oxygen. So which one of these does that match? If we check the data table, we find that molar specific heat for oxygen was 29.16. Molar specific heat for nitrogen was 29.04. Based on that information, what does that suggest about the number of modes?
They both have modes active.
Yeah, it looks like this is both of these are a pretty close match for 29.1. There's a little bit of discrepancy between these because this is really just an approximation. This is a very close approximation. 29.1 is very close to both of these. But we can assume that in this circumstance, these molecules have all their modes active. In other words, this data was taken from a measurement in which all the modes were active, so presumably a very high temperature. But if you took the same measurement at a more medium temperature, you would get about 20.8 instead. And if you took the same measurement at a very low temperature, you get about 12.5 for the specific heat instead. And of course, it's not an instant transition. If you start with very cold oxygen and find that it's 12.5 as the molar specific heat, and then you gradually warm it up, it's not going to go through a sudden change to 20.8. It's not going to go through a sudden change to 29.1. Instead, if you actually measure temperature versus heat capacity, at very low temperatures, it is going to be 12.5. At medium temperatures, it's going to be 20.8. And at very high temperatures, it's going to be 29.1. So it's going to pass through these points. But it's not going to be an instant change. It's not going to go like 12.5 for a while, and then suddenly jump up to 20.8 for a while, and then suddenly jump up to 29.1 for a while. What's actually going to happen is it's going to be more of a gradual transition. It's going to be 12.5 for a while, and then sort of ramp up to 20.8, and then ramp up to 29.1. The reason for this is because even though an individual molecule can't be anywhere in the in-between values, any one molecule is going to be 3 or 5 or 7. For a diatomic gas, there are no other options. You can't have 4 modes per molecule. You can't have 6 moles per molecule if it's a diatomic gas. You can't have anything more than 7. You can't have anything less than 3. It's 3 or 5 or 7. Those are the only options. But in this formula, number of modes isn't exactly the number of modes of one specific molecule. This is the average number of modes. So can you think of any circumstances where the average would be somewhere between 3 and 5 or somewhere between 5 and 7? What would cause that to happen? If every molecule has to be 3 or 5 or 7 and those are the only options, how could you get an average that's somewhere in between? How do you typically calculate an average value? Like if you just got a bunch of numbers and you want to find the average, how would you calculate that? Yeah, you add them all up and then divide by the total number of things. So if you've got, let's say, 1 million molecules, and each molecule is either 3 or 5 or 7 modes as the only options, if you add together 1 million 3s or 5s or 7s and then divide by 1 million, the result could be anywhere between 3 and 7. So you can get the in-between values if some of the molecules are still frozen out and some of them still have their modes active. So if you're adding energy, let's say you start with all the modes frozen out except for translational, and you gradually add energy, you get to a point where some of the molecules are now at 5 because they have enough energy to rotate, and the rest are still at 3. The average will be somewhere between 3 and 5, even though each individual molecule is either 3 or 5, nowhere in between. So you're gradually increasing how many molecules are at 5 versus how many are at 3. At this point, they're all rotating, or at least almost all of them are. There might still be some that don't have enough energy. When you get to this point, you're now adding more energy, and you've added enough energy that some of them can start vibrating, even though most of them aren't. So the average is a little bit more than 5 modes per molecule. And then more and more of them start vibrating. Eventually you get to a point where they're all rotating and vibrating, and now you have maxed out the molar specific heat. But the molar specific heat does change as the temperature changes because you're activating more modes. You're allowing more molecules to activate those frozen out modes, little by little. Any other questions on that? All right, have a good weekend, and I will see you next time.
Thank you.
You're welcome.